So, hello everyone and welcome to this third SELGRA webinar. I'm very excited to have you here today with us. My name is Jeremy Rabino and I'm the president of SELGRA. So for those of you who are not familiar with SELGRA, we are the student chapter of the European Low Gravity Research Association. And today I'm very proud to welcome you to our first intercontinental webinar with Professor Karl Hasenstein, who is calling us from the US. And I hope that you are as excited as I am. Karl is a specialist of plant biology, and especially their perception and response to gravity. After a PhD at the University of Saarland in Germany, he spent most of his career in the US. He completed a postdoc at San Diego University and at Ohio State University before finally coming to University of Louisiana at Lafayette. He still works there now, and he's there a full professor. Karl, in addition to this, is also a visiting scientist at the Kennedy Space Center, and he completed 2 space experiments, one on a space shuttle flight, one on a SpaceX flight, and he's now working on a 3rd space experiment. So today he will share with us his experience about clinorotation, from its concept, the results it can provide, but also the problems that can arise and how to solve them.
Good afternoon, good morning, wherever you are, and whatever appropriate time it may be. I'm happy to give a brief orientation on clinorotation and what you can do to maybe start conquering the world of space biology. So I try to explain a few things that are essentially related to clinorotation, and I will try my best to answer questions that you may have. So let's go and start with a brief overview. Because gravity is so ubiquitous, it is difficult to assess its actual effect on biological systems, particularly on plants, because they have a slower response time. If you stimulate a mouse or ourselves, you know, this is a very quick response. In the case of plants, this is more difficult to assess because the response is of a longer duration. So, of course, as a scientist, whenever you want to study something, it makes sense to remove it from the environment that you intend to study. So removing gravity is next to impossible. Of course, we know that we have gravity compensators, and one of those is going into space. And you do not really remove gravity, but you counter gravity by flying around our planet so quickly that we are in a continuous free fall. And that free fall is the equivalent of what some people call microgravity. It is really not microgravity, it's just the balancing of gravity with the centrifugal force of whatever moves around our planet. So the other thing that is important is to realize that space experiments are not really just about eliminating gravity, because that simple fact has additional problems. And so it's important to point out that space effects are not just linked to weightlessness, which is the better term rather than microgravity. So we need to look at the consequence of not having effective gravity conditions, and that affects the buoyancy of gases, of liquids, the fluid flow that we are accustomed to when we spill a glass of water on terra firma. This is very different from doing this in space. But also gas exchange is limited. And in addition to this, the environmental condition, especially on the ISS, our essentially only space experiment that or space laboratory that we know of, the environmental conditions are quite different from what we are exposed to here on Earth. For example, there's an extremely high CO2 concentration and also an extremely high concentration of volatile organic compounds. And so this also affects the biology that functions in this environment. So because it's so difficult to get into space, we are always on the lookout for some alternative approaches. And as everyone knows, Clinorotation is the go-to methodology that attempts to remove directional gravity effects. It cannot remove gravity, but it can attempt to remove gravitational effects. The other thing that it can do, or that we can strive to do, is to simulate gravity levels that are not the 1G level seen on Earth, for example, for Moon or Mars. But it also, this Clinorotation has some competition, and I will briefly go into this and talk about magnetic levitation, because it's another approach to negate gravity, but with a force that is very different. I'll show you a brief example of this. Now, despite all the benefits, we cannot forget that Clinorotation also has its costs. And the costs are not the monetary costs, but the physiological costs that I'm talking about here. So that means we need to consider enhanced mechanostimulation, because this continuous rotation is having its own effect. And the adaptation to this mechanostimulation also changes the responsiveness of plants in particular to this type of activity. So the effect of energy and frequency that is pumped into a system by virtue of continually rotating it is of significance. And for that reason, not just Clinorotation, but in the entire simulation approach lends itself to interdisciplinary approaches. And that is very important, because it is relevant to engage biologists as well as physicists and chemists and bioinformaticians and so forth to the problem of Clinorotation and what it can do to educate us about space-related activity. So this is the overview. I go into a few examples just showing that you have not just a response in plants that you see visually, as in the little video on the right-hand side, the Venus flytrap that moves rather quickly, but invisibly. And this is shown right here on an Arabidopsis plant that was simply squeezed. And you can see the traces of it, but only when you process the tissue and look, in this case, at the expression of a particular gene. But this physiology that occurs in plants is so diverse that it cannot be summarized in one thing and cannot be assessed readily. All these conditions change the response to gravity as well. For example, the jorquette that you see in this particular picture here changes the growth direction from a vertical to an angular orientation of the branches. And all these things are subtle, and you don't know when that response has a different set point. So that is important to remember. As we know, gravity sensing depends on something that interacts with mass. And I cut through the chase here. We know that the most important, but not the only factor in gravity sensing is the sedimentation of starch grains. It is also shown that the buoyancy of vesicles is important, in particular in a different type of organisms, in phycomyces or fungi in more general terms. The disruption of cytoskeletal structures can have an effect and maybe even dense and massive nuclei that you see right here that are typically tethered and do not move, but that does not preclude that they can have an effect on the gravity sensing. And there are other things that we just don't know enough about, but we cannot really preclude that we know everything that affects gravity on a cellular level, that affects gravity sensing. So the study of gravity is typically related to root gravitropism. And you see the typical textbook rendition here, an Arabidopsis root growing and making this very obvious 90-degree turn. But when we look at other things, you can see that this is not so common, because you have initially a response in the tip, and then that straightens, and the main curvature takes place elsewhere. So there are diverse responses known, and how they all respond to Clinorotation is an interesting topic that requires much more time than anyone can do by themselves. So I appeal to you that you can collaborate and tackle these questions in different or several groups. So when we, as I mentioned earlier, look at alternatives for the approach to negate gravity, we can utilize high gradient magnetic fields. They are important because they exert an effect on biological systems, which is shown here on the left-hand side. You have essentially your body, or any biological thing, is mostly made up of water, and water is a diamagnetic compound, and the degree of diamagnetic susceptibility makes it possible to distinguish dense materials such as starch from less dense materials such as water, and combine all this, and you obtain an effect that is counter to what you would think when you see your common magnet at work, where you have a strong force experience that is typically related to ferromagnetic behavior. Somewhere in between are the so-called paramagnetics, but I don't want to discuss this. I just rather show you these little videos that are the response of putting biological material, you see what it is, a little frog and a strawberry and just plain water, into a vertical bore of a very powerful magnet. And these magnets are capable of producing the gradients that then levitate biological material. The energy requirement is such that only small things can be levitated. So it's not possible to do this on a larger scale. This is the big problem with this, but we can certainly construct containers that allow the response of little Arabidopsis seedlings, for example, under these conditions. However, the cost in this case is that you have to cope with the effect of the strong magnetic field, and that has its own problems. So we go back to the chance of coping with gravity by using Clinorotation, or in this case, an example of high gradient magnetic fields in space. And I want to share with you a brief video that illustrates what happens when you, when you do space experiments, because initially, although a movie is playing or an experiment is forming, you don't know if it's going to be successful, and you have to wait for a long time. I cut this time from 2 days short to a few seconds, and you see, at least on the left-hand side here, this root growing and then encountering the origin of this high gradient magnetic field by virtue of having this wedge inserted. And the response was quite clear. A movement away from that high gradient magnetic field. And the last step that you saw is simply the effect of fixation in space, that we can study what happened with this. So this is costly and very difficult to prepare. We have to look at different methods, and that is Clinorotation. You may have seen something like this in the past. On the left-hand side, this is what we impose on a cell or an organism. On the right-hand side, you see the perception that is experienced from the actual organism or the cell, as it is shown right here. The point is that the continuous rotation confuses the response mechanism such that it eliminates a directional response. You can experience something like this when you go to certain joyrides on fairs and so forth, and you go into a centrifuge. You observe the exact opposite. You can be pinned to the wall, figuratively speaking, by virtue of the centrifugal force. If you can stand the rotation as it is shown right here, you typically get pretty sick, and that's an experience that some people enjoy. Anyways, this is as close as it gets to your own or our own experience of Clinorotation. So in terms of plants, it's important to realize that in particular, the beginning of a rotational event causes a very strong memory effect that lasts up to 2 hours, that has been investigated. And it's important to consider this and not just use one single type of rotation. So what are the choices that we have? I give you a few basic pieces of information that are supposed to illustrate what we can do. So I show here on the right-hand side in this circle 3 different scenarios of rotation. So the horizontal rotation, this blue line, is what we consider with the typical clinostat to be an equivalent to free fall. This can actually be obtained when we look at the sedimentation pattern of particles in cells or small volumes of water or some dedicated environment. When we go to the full 90-degree rotation, we have not eliminated the effect of gravity because it is present in, say, full force, but we have superimposed a movement, a rotational effect, and at least to some extent, this is a suitable control for Clinorotation because we have Clinorotation minus a particular gravity effect. So we continue to expose these test objects to 1G, but we superimpose to that experience of sorts the rotational effects. In between, shown in green here, is what we can do to manipulate the system to obtain partial gravity. So all it takes is take an incline that is, say, 1 meter long and raise it 16.5 centimeters, and we obtain an angle of 9.5 degrees. And by doing so, mimic the gravity value that exists on the moon. So we have 0.16 G equivalents. And the same is true for Mars. We have an angle of 22 degrees, raise our 1 meter long incline by 38 centimeters on one side, and we obtain an equivalent for Mars G values. So this is the manipulation that you can obtain simply by superimposing to a Clinorotation a certain angle. But you can also achieve a similar situation by changing the timing of rotation. And this is an attempt to illustrate this here. We have a sinusoidal representation of a full rotation. And when we arrest anything at a particular point along this circle, that particular orientation is going to be responded to or presented to the organism for the ratio of the total duration versus the position at which it is at standstill. And so we have two ways of achieving different effects, different G levels on biological systems. So this is just an introduction to the complexity that we can achieve when we look at rotation. On top of this, we need to be mindful of the speed of rotation. So this diagram is supposed to illustrate this, and I show you a few pointers here. We consider the radius against the rotational speed. Either omega is expressed as revolution per minute or radians per second. This is easier to calculate. This is easier to relate to. So when we have so-called slow rotating clinostats, we have to be at less than about 5 RPM in order to not exceed a milli-G gravitational effect by virtue of centrifugal forces. So this is important because it determines the size of something that can be exposed to a meaningful reduction of G effects. That has to be less than 15 centimeters if your RPM is reduced to less than 10. Typically, the typical clinostats use either 1 or 2 RPM for convenience sake, but you can go a little higher if you compromise on the level of exposure or treatment, so to speak, of gravity equivalence. Of course, when you have very narrow volumes, such as algal or bacterial or unicellular suspensions, you can go to a higher RPM value, but you still maintain a reasonably low G level. And this is shown right here in this pink area. So there are flexibilities that have to do with the centrifugation and the rotational effects. And this is important because it limits the size of meaningful clinotation. You sometimes see images of really large constructs in order to, accommodate larger plants. But they have the big disadvantage of having an ill-defined rotational condition because of the sheer size of the platform on which an experiment is performed. So this is a reason for going to relatively small instruments. And I show you the clinostat technology. You see on the left-hand side a big clinostat that happens to be rotating one of my space experiments, and it has its own problems. On the right-hand side, you see the first version of the clinostat that I have constructed and that I will be showing you a second version of. So with that, I can only say when you have large clinostats, you are subject to many problems. One is that this entire mass has to be moved by a fairly strong motor. And if the motor is not constructed properly or doesn't have a gear, you have vibration that causes tremendous problem. When you go to what you see right here, you have a much smaller volume, but it has a higher quality, and you can see the two independent axes supporting the rotation. This is important because we can control this with proper electronics much better than a system like this. So I would like now to tell you a little bit about problems with these clinostats before I go into explaining how you can build your own. So what I want to distinguish is the randomness of a virtual movement from what we actually see when we have not a random positioning machine, but something that is known as a 3D, or actually a misnomer, nonetheless, a clinostat that has two axes, but they go at a constant ratio. It can be the same, but based on how a belt, for example, is controlling the rotation, you can obtain certain offsets. And these offsets or phase angles can induce what is known as Lissajous patterns. And I show a few of them here, and you see that these patterns prevent the condition from becoming truly random. There is an easy way to produce patterns that you do not intend probably, and for that reason, the response is not equivalent to a true random positioning. So the randomization is important to eliminate complications, as I have illustrated right here. So it's important to be mindful of what is really random movement and to develop algorithms for the two axes that rotate that eliminate this, and at the same time allow the establishment of so-called partial G levels, as I explained them a little earlier for, say, Moon and Mars levels. So with that, I can show you what it takes to build a random positioning machine. You got to design it properly, and I highly recommend that you go for autonomous movement, meaning you don't want something that is dependent on a computer that controls it all the time. And the reason for this is that it ties down the machine and your computer, and it also introduces other problems. When the computer is misbehaving because some software is being installed, it causes unforeseeable problems that make these types of interactions problematic. You would also want to consider illumination, as you may recall from the previous video that I showed, and this is important to eliminate only the effect of gravity, but not the effect of continuous illumination based on petri dishes or other volumes that you make available. Lastly, it's important to keep in mind the versatility of these systems. And when you have a computer controlling this, it is possible, but it becomes a bit more complicated. You need to develop a frame that can house whatever your payload is, so to speak. And you have to plan for a control system. And the control system is, in essence, a dedicated computer that should be programmable. It should be robust and flexible, so that you can manipulate things if you see the need for a change. It needs to be capable of changing the angular velocity, meaning produce different types of rotation. And you also need to keep in mind what kind of motor type you use, or the power that the entire system consumes, and the power supply that you have. And most importantly, in our context, of course, is the amount of money you pay for this. When you look at commercially available systems, provided by a company in the Netherlands and another one in Japan. The cost is prohibitive for most of us because it runs into the, I think it's around $50,000 per such equipment. What I am talking about is a fraction, a small fraction of that price. You can get away with less than probably $500, maybe less than 300. So I will show you what this possibility looks like, and I will now switch to a different screen so that I can illustrate this a little bit better. Here is my drawing. Actually, what you see on what you have seen in the previous slide, it has individual components that are 3D printed, and wherever I point at here is one element. I can also highlight it, and you will see that we have motors, two motors here and there, and I can highlight them. And these motors are essential for the rotation of the outer frame and the inner frame. But both motors are programmed individually by things that are actually housed in this box here that contains all the electronics. The system is built so that it can be printed on relatively small 3D printers and then be stacked or mounted together. You see here this screw holes that are needed in order to attach the top to the bottom of this frame. On the inside, you have not just, I need to rotate this a little bit better, an inner frame that rotates, but you have this panel here that has LED lights provided, and you can assemble these very inexpensively again with a light source of your choosing. It can be white light, it can be blue light, it can be red light, it can be a combination of this, and you can study light effects on Clinorotating systems. The actual payload is shown right here. It's a frame that you have seen on that brief video that houses one or several petri dishes, but you can also change it by going to a different system, such as a closed sample box that I show right here. And the sample box can be mounted inside this frame or between two of these frames in the ridges that you see right here. This frame is approximately 10 by 10 by 10 centimeters, and I have one, unfortunately I can't show it, that is able to record infrared images of roots that germinate, and you can do various studies with this. So this is just a nod to the flexibility of this system. So with that, I go back to the other screen and we continue by briefly showing this very system that I introduced in action. Unfortunately, I was not able to put this in front of me, but you will see different movements of the outer frame and inner frame, and I show you in a minute how I changed this so that this particular system is responsive to short-term changes, but that's not what you want to do for an actual experiment. So the parts that I have illustrated are all available as STL files. This is what you can modify and print without having to worry about whether they fit or what have you. The bigger pieces, as I mentioned, consist of two units that are mounted together. The mounting is all done with the same type of bolts, M3 or 3 mm diameter screws or bolts. And the control in that box that I pointed out is based on Arduino Nano controllers. They're very inexpensive and they provide programmability for each axis. They have low power consumptions and are completely programmable, so in very different ways. In terms of the motors, I'm working with stepper motors, but it's also possible to use servo motors. The Arduino can handle both types. It becomes a chore to discuss in detail the different types of motors that are available and which one you should choose. It depends largely on the power supply that you have and the mass of the material that you want to rotate. So this is one of the challenges of a call it homebrew type system, where you have to prepare things ahead of time because you need to custom design everything else around your specific requirement. A ready-made system takes care of some of these considerations for you because they typically are or provide greater latitude for these types of activities. So when we consider this, I show you briefly what it means to control this system. So what I have used is the Arduino Nano. It's not as big as what you see right here, but I tried to show you one in a second. And this thing controls a so-called driver, which is a tiny little piece of electronics that is actually talking to your stepper motor in my case. But you have similar drivers that are suitable for servo motors. I should make a remark on the difference. The stepper motors have the ability to move, as the name implies, in steps. So when you go at a slow step, you get a little jerky movement. You can eliminate this by so-called micro-stepping with this system. The system is capable of doing down to 1/16 of a step, and that smoothes out any jerky movement. The servo motors, on the other hand, don't have to contend with this because they have a different way of positioning or knowing at which cycle in a rotation they are. They are smooth, completely worry-free in terms of any motion problems. So when you look at this, you may be interested at the programming. And what you see here is actually the entire program that is needed to run the system. I know this is a lot of text, but not that much actually. You need to set up the system. There are between these double slashes comments what it means. It defines terms that are needed to define the rotation, for example, to define the speed, to define the rotation of the duration of the rotation and so forth. But also it defines how the microcontroller, the Arduino, talks to the motor. This is shown in this section. The actual program is shown right here. This is a loop that keeps on cycling through this as long as you want the system to run. This can be for a few minutes, hours, days, weeks. My longest that I have done so far is 8 days, and it works fine. I had no problem with it. The problem, of course, can be that you have a power outage, in which case you are doomed when you use a computer because they will not restart. Your experiment is lost, but these types of Arduino-based systems just continue to rotate as soon as the power comes back on. So what I did change on the little video that I showed you previously is just this one line here. This random number times 4,000 determines 40 seconds actually of timing that elapses before a change in the rotation takes place. I changed this to 4 seconds so that you could see these changes taking place. I would not advise this for an actual experiment. Anyways, this is very simple, and all it takes to make the system work. The other thing that's important is that you need an experimental record. And once again, I have used a nano system with a micro SD module that I use as an accelerometer. The actual accelerometer is shown right here. It talks to the Arduino, and it in turn writes this to a micro SD card. This is a system that can be built very inexpensively for a cost of probably less than $20, but it is a little bit heavier. So you can obtain this, including power supply, for about 20 grams. And the cost, as I said, $15 to $20. On the right-hand side is an alternative that is just becoming available. And you may want to Google this if you're interested. This is a small, about an inch, a little bit bigger than an inch in diameter system that has a collection of 10 sensors, but it communicates with a Bluetooth system. This is the Bluetooth antenna that is simply being inserted in the port here, and the system starts to operate similar to that one simply by inserting one of these coin cells on the backside of this unit. This thing is also programmable, and I just received it last week, so I have not been able to actually explore this, but I did test it. You can get an app for your smartphone, and you can trace, for example, the experimental profile, the G levels on that, on your phone. Of course, it is important to realize that while you're doing this, your ability to use your phone as a phone, for example, is limited. Anyways, this is what I wanted to share with you, and I think I'm maybe done with my talk, and welcome your questions.
So yeah, I'm back. Thank you very much for this very interesting presentation and for sharing so openly all your work, Karl. It's actually very exciting to see that thanks to 3D printers, hopefully tomorrow, we all can build our own clinostats.
That's right. That's the idea.
Karl, I know that it's finals week at your university and that you are very busy at the moment, especially because everything has to be organized remotely. So we really appreciate even more the time you took to share your experience with us. I would like to remind people that they can ask their questions in the chat or request to ask their question out loud. You just say, hi, I need to ask a question. Can you unmute me? And we'll do it. Yeah, in the meantime, I already have one question for you, Karl.
Sure.
So you are lucky enough to have performed experiments both in space and on the ground with clinostats. Can you describe a little bit if you noticed some annoying differences in biological responses that justify your need to move to 3D clinostats? And maybe also another question, so you move from 2D clinostats to 3D clinostats. Is there a next step after that?
So this was a lot of questions. I try to go backwards. There is probably not an additional step for this, because although you don't have a complete gimbal configuration where you modify all 3 axes, this would be the ideal scenario. You get a complete coverage of the space that you want to explore, meaning all 3 dimensions, by virtue of having 2 axes as I illustrated it. But theoretically, you could go to a motility for 3 axes. That is possible, but I believe it is not necessary. So in terms of putting a clinostat in space, I don't believe that this would be meaningful. What is meaningful for space experiments is to put a centrifuge in place. Some experiments, some hardware has that ability, and the idea simply is to eliminate, in this case, all the effects associated with weightlessness, but maintain the condition of space otherwise. And I alluded to some of those at the very beginning. So that is why it is important to have a so-called control, meaning a 1G or partial G centrifuge in space. There are other experiments, for example, partial gravity experiments that can be done in complete microgravity by adjusting the rotational speed accordingly. So I hope that this answered your question.
Yeah, thank you, Karl. We also have a question in the chat from Daniel, asking if you are thinking in upscaling your design to accommodate more replicas at the same time.
Well, there are 2 approaches. You can have, for example, this experimental volume fully occupied, and you can have a stack of about 8 Petri dishes available. Or you can, because this design is so inexpensive, you can run several of these machines at the same time and expand your capability this way. This is also advantageous in case one of the random positioning machines fails. And once you have built one, another one is not that difficult to put together.
Okay. I also have a question from Tobias from University of Colorado at Boulder. So he said that clinostats and rotating wall vessels are both devices for simulating microgravity. Can you elaborate a little bit more on the differences in application between these 2 devices?
Yes, the rotating vessel is operational only when you have liquid environments inside of them. So this is fundamentally different from something like, say, a seedling, where you actually interact with the environment in its original form, meaning gaseous environment. However, if you cultivate algae, for example, or unicells, you can provide a liquid environment, and that lends itself to the rotating vessel. There is a considerable amount of theoretical information available that indicates that for the rotating vessel, which is essentially a one-axis clinostat, you can achieve better microgravity analogs than you can do on a single-axis clinostat. I did not go into this, and I have not contemplated this theoretically, but I would assume that a random positioning machine for unicells is essentially overkill. You do not need it if you have a suitable rotating wall vessel available. This is an incomplete answer, but the best I can do right now.
Okay. We also have a very interesting question from McGill. So, which is that when you have a large platform or large sample, are there any differences if you place, if you have a sample exactly in the middle of the loading platform, or if they are a bit distant from the middle? And if there are differences, what's the best way to avoid this?
This goes at the core of the problem of any clinostat. And this is why I showed you this diagram on one of the slides. When you extend the radius too much, you introduce centrifugal forces. And these forces produce artifacts. That is why I firmly believe a 3D clinostat or a random positioning machine should be relatively small. When you go away from the center for which all the computation was done, you introduce artifacts by virtue of superimposing to the intended randomization some kind of centrifugal force. And this is a problem. I should point out, however, that essential experiments have shown by Ruth Hammersbach's group in Cologne in Germany that obviously for random positioning machines, a higher angular velocity is desirable than for simple axis clinostats. And the consensus seems to be based on her research that an angular velocity of about 60 degrees per second, this is the sum total for the two axes, is suitable. That means instead of having a 1 or 2 RPM system, you would have an 8 to 10 RPM system. But keep in mind, this is divided between the two axes. So of course, when you go to a higher velocity, then the displacement away from the center of your experimental platform or defined volume becomes more problematic. So the safe bet is when you go to a lower rotational speed, you can occupy a larger volume.
So thank you for him. We have another question from André asking if it's possible to use clinostats to do experiments in fluid mechanics and dynamics.
The short answer is yes, absolutely. You just need to know the boundary conditions. So it matters whether you use a round vessel, and you go back to what we discussed a minute ago, the rotating wall concept, or whether you use a different shape like square profiles or even more complex profiles. This is a fascinating topic because it lends itself to the study of water flow that is no longer controlled by gravity, but by surfaces. This is important for water delivery situations in space and so forth. It's a fascinating topic, and I could talk for a long time, but I just say, yes, you can do these types of experiments on an RPM system.
Okay. We have also a question maybe more about the design you suggested for clinostats. It is how do you ensure that environmental conditions such as exchange of gases in your samples, no, sorry, how do you ensure environmental conditions in your samples while avoiding leaks?
While avoiding?
Leaks. For instance, for exchange of gases.
Okay, so I showed you briefly this, it was a blue box, and you can construct this in a gas-tight environment if you want to, say, study CO2 levels. However, this is a dynamic system, and plants, for example, consume CO2, not so much in the dark, but if you put the light in place, then yes, that will change. You have two solutions to the problem. You can put the entire clinostat in your chamber with a desired environmental condition, including gas pressure or composition. So this is not a showstopper, but you need to be concerned with a system that contains it. So what you saw on my diagram and so forth is relatively small, and you can get, or you can build a small gas-tight chamber and put this into it. That would be one solution.
Okay, I think that we reached the end of this first SELGRA webinar. I would like to thank again Professor Karl Hasenstein for preparing this presentation for us. Also you for coming to this online event. This webinar will soon be uploaded online. So if you enjoyed it, don't hesitate to share it with people who might be interested. You can also have a look at our previous webinars on the YouTube channel of SELGRA. And if you want to be notified about the next webinars, you can follow SELGRA on Facebook, Twitter, Instagram. If you are a student, you can also visit our website and become a member for free. If you are no longer a student, then you can have a look at ELGRA's website also. This being said, thank you very much again. I wish you all to stay healthy and safe, wash your hands, eat your greens, etc. And we'll soon meet again for another SELGRA webinar. Bye-bye.
Bye-bye.